Alrighty, let's take a minute here or five or so and think about atomic mass. Let's talk about atomic mass and what this means, right? We already know a little bit because we've talked about uh, massive stuff. Um, when we're thinking atomic mass, we're going to think in units called the atomic mass unit. Okay, this is a little bit of a weird unit, but it was defined in such a way to make things easier for us. And roughly the idea here is that one proton is about the same as one neutron, and this is about the same as one AMU. So knowing what the mass of something is in AMU um, will give you an idea of how many particles we're dealing with in the nucleus. Okay, our official definition is up here. This is a 1 AMU is 1/12 the mass of a carbon-12 atom. And now we realize from our previous video about isotopes that a carbon-12 atom has 12 particles, right? This is 6 protons and 6 neutrons. Okay, so with 12 particles total, 1/12 of the mass of 12 particles is one particle. Okay, 1 AMU is approximately 1.6605 times 10 to the minus 24th grams. I'm not writing it down because I don't think it's important for us to stress about it. Okay, you can kind of see it here. Uh, the proton and neutron, their mass in AMU is a little bit more than 1 AMU, and they're very slightly different, which is something we can use to our advantage at some point eventually. Okay, um, and just remember that electrons are much, much, much smaller than protons and neutrons. And for chemistry purposes, we essentially assume that uh, electrons don't have a mass. Okay, I know that seems weird, but that's kind of how we work with stuff. Um, yeah, so when we talk about atomic mass, we have to talk about mass spectrometry, and this may not completely jive with what we're thinking about, but we're not going to go into huge detail. If you make it into organic too with me, we'll talk about mass spec in a lot more detail. But um, for now, we're going to look at it just from an atom's perspective. Um, this is for measuring mass, and it measures mass very, very precisely. Okay. Not only that, but we can sort things by mass. So here we're looking at um, a sample of neon, and it has been sorted into three isotopes: neon 20, neon 21, and neon 22. Okay, we really get two pieces of information out of the mass spec. But how this works is you're going to put a gaseous sample into here. It gets ionized by powerful electricity. Okay, essentially this is ripping electrons off of the atom so they have a positive charge. Then they're passed through an electric field to accelerate them. They're fired through a magnet, and the magnet puts them in a curved field, and they deflect based off of the mass. And so where they hit on the screen is relative to what kind of mass it is. Okay. The detector here is very, very sensitive, so it measures um, the exact isotope, and it can tell the difference between 20, 21, and 22. And you can get a lot of precision out of mass spec, but we're not really going to. Well, I'll show you some data in a minute that has some really high precision to it. Um, so that's what we're getting out of this. What we're getting out of, what's the next slide? Yeah, okay. We're getting out of the mass spec is two pieces of information. We're getting the average atomic mass, which is what we just refer to as atomic mass most of the time. It's a weighted average of all isotopes masses for an element, and this is naturally occurring isotopes. Well, I guess maybe not even naturally occurring anymore, but stable isotopes, whatever. All the isotopes of an element and its weighted average. And I'll show you how we calculate that and what that is as we do stuff in a minute here. The other piece we get is this natural abundance, and we're going to need natural abundance to think about the weighted average. Natural abundance tells us how much of a naturally occurring sample is that particular isotope. So here what we're looking at is to say the neon 20 isotope is roughly 90% of all neon. Neon 21 is 0.27 and neon 22 is 9.25. Okay. And this is the case with most elements. If you dig into the data uh, in detail, you can see most elements have one or two stable isotopes that are mostly abundant, and then several smaller ones, several less abundant ones that have different masses. Okay. Um, And there's a handful that don't really follow that pattern, but we're not going to stress about it too terribly much. Um, I just want us to know what atomic mass means and what natural abundance means. Okay. Something to remember here with natural abundance, we're measuring the percent of a total sample or the fraction of a total sample. So the total, I totally spit on my screen. The total abundance, you're getting me unedited for this because I don't have time for that. So just enjoy the weird. Um, the total abundance, it's 100% of the sample. Or if you're coming at it from a fraction, this is 1.00, or an exact one. Okay, so and we'll need that to know that information as we do some stuff. All right, let's do some stuff. Um, Here's an example. Let's use this data to determine the atomic mass of chlorine. All right, chlorine is one of those ones that doesn't follow the pattern I was just showing, and that it's a halogen, and halogens do this a lot. There's two main isotopes of chlorine, chlorine 35 and chlorine 37. Okay, one's roughly 75% and one's roughly 25%. So this gives us some data to work with. When we're looking at the weighted average, what we're doing is we're going to multiply the mass of an isotope times its abundance. And then we're going to add for all isotopes. So one way to say this is we're going to take the sum of mass times abundance for all isotopes. Okay, and this is going to equal our atomic mass. So it's not that doesn't say atomic mass. I don't know what that says. It's not a direct average. Okay, so I call it a weighted average because it takes into account how abundant things are. You can also figure out what's the most likely abundant isotope by figuring out which isotope mass is closest to the atomic mass, because then that one would probably be the most abundant. Anyway, so what we're going to do is we're going to multiply the mass times the abundance and the mass times the abundance. And I should have written this down here, but I'm just going to come down here and do this. Okay, mass times abundance for the first one is 26.49240076 AMU. I'm leaving a lot of digits on here. Remember when we talk about sig figs. And then for chlorine 37, this is 8.96053416 AMU. Okay, and we're gonna have to add those together. Okay, when we add them together, we get 35.45293492 AMU. I don't usually ask you to do this, but it's nice to see where it comes from, and you're going to have to do this in the homework at some point as we do it. If we look at this, both of these are limited in significant figures by the abundance, because the abundance has 4 significant figures. So each of these numbers has to have 4 significant figures. That would be ending with the 9 here and the 0 here. Then we're adding, and when we're adding, we're thinking about decimal places. This one has 2 decimal places and this one has 3. So our answer should have 2 decimal places. So when we round this dude, we get 35.45 AMU. Units on everything, looking nice. Okay. Does that make sense? You can also kind of back calculate abundances or masses of a particular isotope if you know the atomic mass or don't know the atomic mass. You can algebra some stuff out. And we might see some of that stuff in the homework, but it's not stuff I would ask you to do on an exam. All right. One more example. Okay, so another halogen, bromine. Bromine is 2 main isotopes, bromine 79 and bromine 81. Okay, we know the abundance of bromine 79, and we want to know what is the abundance of bromine 81. All right, remember what we said about total abundance a minute ago? Well, the total abundance is 1. Total equals 1. We know there's 2 isotopes here, so 1, these 2 things have to add up to give us 1, right? So 1 minus 0.5069 gives us 0.493. 81. And so this is the abundance of bromine 81. There's no unit here because this is a percent. This is just a counting of the things. Um, right. So roughly, I mean, bromine is roughly 50, 79, and 81. And again, when we get to organic chemistry, we'll make use of that and the chlorine fact as we look at mass spec in more detail. All right. If you have questions, get a hold of me, and I'll catch you later.